Okay, here's our starter problem. We've got like a it's called a flywheel, or if you've ever done any pottery or anything, you got like a pottery wheel. But you've got this wheel. It's just a cylinder. Okay, and we're going to apply a net torque of 20 Newton meters to it. The radius is 0.35 meters. The mass is 3 kilograms, and it's going to start from rest. And I want to know, what is the rotational inertia? What is the angular acceleration going to be? What is the final angular velocity at 10 seconds? And what is the change in angle in revolutions at 10 seconds? Okay, so let's get started. Rotational inertia, I. Well, if you look it up, for a disk, the rotational inertia, I, is 1/2 mr squared. Now, I will give you the equation on the test, okay, for rotational inertia. You don't have to write it down. You just get this from the table, though. And notice, here, this is what's always going to be true for rotational inertia equations. It's always going to be some fraction of the total mass times the total length, or some linear aspect that describes the object, in this case the radius. And notice that the thickness doesn't matter. Like if this had a thickness of I don't know, call it L, that won't affect the rotational inertia. It might affect the total mass, okay, but it's already included in there. Okay, so now all we have to do is plug in our values. 1/2, the mass is 3 kilograms, and the radius is 0.35 meters. And we're going to square it. And so we plug our values in, 0.5 times 3 times 0.35 squared. And I got 0.184. We'll round up to 3 significant figures. And what should the units be here? Really easy. What are the units for this answer? Kilogram, meters, squared. This will always be the units for rotational inertia. Kilogram, meter squared. Always. Now let's do part B. Well, the net torque on an object is equal to I, the rotational inertia, times the angular acceleration. It's kind of like F equals ma, but for rotating objects. So now I know what the net torque is. That's given. I know what I is from part A. So the angular acceleration equals the net torque divided by the rotational inertia. This is 20 Newton meters, but this is 0.184 kilogram meter squared. And so when I get the value here for alpha, so I'm going to go 20 divided by 0.184, I get 109 radians per second squared. Now, let's take a look at units here. How do we know this is radians per second squared? Well, a Newton is a kilogram meter per second squared. And then we have times a meter, and then we have divided by kilograms meter squared. So if you look at units, you have meter times a meter. That cancels with the meter squared. The kilogram cancels with the kilogram. You have seconds to the negative 2, which is 1 over seconds squared. But we're dealing with rotational inertia, angular acceleration, and torque. Torque, we've got an R in there. And that R, that's where that radian comes from. And so it's really radians per second squared. You can kind of stick that radian in there when you need it. So this is our answer for the angular acceleration. Now, that's very high acceleration. And look, this probably is hooked up to an electric motor. This disc is probably hooked up to an electric motor. You flick that motor on and it comes up to speed really fast. Now obviously you don't want to leave that motor on for too long, because now if you assume a constant angular acceleration, we can figure out the angular velocity at 10 seconds. Now, how did I know to use this one? Because I know this, and this is given, and this is what I'm trying to find. So what am I not given and I don't need yet? The change in angle. So this is just like the kinematic equations we used before. So this is going to be 0, omega naught is 0, plus 109 radians per second squared times 10 seconds. So we're spinning at 1,090 radians per second. That's really fast. And then for part D, well, if we assume a constant angular acceleration, and I really should state that in what's given, alpha is a constant. Okay, the torque is the torque is a constant, so the angular acceleration will be constant. But anyway, part D, well, what do I know? The initial, I know angular velocity, the time, and the angular acceleration. So I'm going to use the third kinematic equation. Now this is 0. So this is 1/2 109 I'm sorry, 109. Radians per second squared, but times 10 seconds squared. And you get, yikes, 5,450 radians. That's the angle. That's the change in angle. I went through that many radians in only 10 seconds. But we want that in revolutions. Well, there are 2 pi radians in 1 revolution. Remember that? That conversion from revolutions, like how many radians are there in 1 revolution? Well, there's 2 pi radians. And when you divide that by 2 pi, you get 867 revolutions. Now, if you got through all of that, I forgot to box my answer here. If you did all of that on your own, you're ready for that part of the test. That's really good. But this kind of, notice this kind of has a little bit of everything that we've done so far in this unit. Rotational inertia, net torque, and then the kinematic equations for rotational motion. So this is a good problem to study. Any questions? You all agree with those? So check my arithmetic. Okay, that is all.